So thanks for the invitation. So I'm going to talk about today about problems that we encounter when we deal with medical image analysis with deep learning, and basically propose some solutions to these problems. So this was the initial plan on the abstract. So we had 3 applications, which were mammography, classification for early breast cancer diagnosis. Then I will talk about PET image registration. And in the abstract, I mentioned organ segmentation. I think it won't fit. I have the slides, but let's see. If I cover the first 2 topics, I think it will be good enough. So I made a balance between not too technical and hoping to reach the largest community. If you want to reach out for more technical details, don't hesitate. Okay, so one of the problems we encounter when we are dealing with deep learning and biomedical applications is that we have really few data compared to natural imaging. So, for instance, in the case of the breast cancer diagnosis, our database is slowly growing, but we are around dealing with an in-house data set of 3,000 images. In the case of this PET imaging for longitudinal response monitoring, we are dealing with pair of images for 110 patients, so this is not huge. And in this organ segmentation, we are in the order either of 44 patients, which is really low for deep learning applications, or 20 patients in the case of cardiac segmentation. On the other hand, another challenge comes from annotation. So when we are able to collect annotations from images that are already there, then it's easy. But usually these annotations are only concerning the whole image. It's very rare to have databases where doctors have delineated the regions that are problematic, for instance, here for this diagnosis of breast cancer. When you do longitudinal monitoring, this gets even worse because, for instance, in the application that we are going to talk about, we have multiple lesions, and it's rare to have lesion segmentation. And moreover, we don't have the correspondence between the regions in the initial image and the follow-up image. And here for the organ segmentation, it's common to do segmentations when we want to actually segment volumes. And sometimes we just don't have any annotations at all. So another common problem that we are confronted in our lab is having few annotations. So small data sets and few annotations are basically the motivation for all of the works we are dealing with here. So let's start with the first one. So here we are going to talk about early breast cancer diagnosis, and we are dealing with mainly 2 tasks, classification and detection. And we are going to address this with self and weakly supervised learning and some graphs. So for the first part of the talk, it would be the work of a recently defended PhD student. So now Dr. Michael Dali, and he's now in the company, and he was already in the company, but now he's the research director of this company that is dedicated to breast cancer. So we have a problem that is quite common in nowadays, because there is protocols across all Occidental countries to monitor women. So we are encouraged to do mammograms every certain number of years in order to early detect the possible development of breast cancer. So here you see, for instance, 4 images where we have an increasing grade of abnormalities according to one classification method that is called the BioImaging. So what we get from clinical data is only image-wise annotation, so they might tell you whether it's normal or abnormal, and the BIRADS class. So for this talk, I'm focused only for this part of the talk on the normal abnormal part. So we have developed quite a few networks that are becoming more and more powerful in predicting this type of solutions. Now the problem is when you want to deploy them, It's usually not that easy because you put inside the image and you get as an output maybe a probability, and it's not so evident to know why this network made such decision. So in the literature, there has been since around 2015 some class of methods starting from the class activation maps, where instead of looking just at the output prediction, you look at a previous layer where you still keep this spatial configuration of the predictions. And in this case, you're able to see that there are some regions that are responsible for the decision that is been made afterwards. So this class activation maps gives you some sort of localization even when you train your network with only image-wise labels. So what we want to do is just a clarification. So now in the rest of my talk, the networks are usually going to be delineated just with some sort of trapezoid figure, such that you know that inside what we have is just convolutional layers and max pooling operations, the typical things that we are now more used to see. So what we are going to do is follow a little bit this diagram of predicting class activation maps in order to explain the decision, and we are going to try to get better at localizing these regions. So the problem with these class activation maps is that when you look at these intermediate layers, usually they have gone through a lot of max pooling operations, so you end up having low resolution. And this is, of course, not desirable. You would like to have a high resolution. In particular, in mammography, you're dealing with images that are usually for medical, for a medical background, they're typically larger, so they're around 2,000 or 3,000. I think in biology is not so considered as a high resolution image, but in biomedical it is. And there has been a trend of methods that build over this class activation map. So if you don't know about this, there is a nice introduction in this website where they talk about BRADCAM and the most recent methods that try to make better activation maps and deal with this low resolution problem. So we are going to take a little bit of a different path. And we are going to first mention that this type of class activation maps can also be understood as something that in machine learning is called multiple instance learning. So this is where you have a bag of instances. And here you could consider that every pixel in this low resolution image is an instance. But you don't know each instance whether it's a positive or a negative. You only know that your black image here has a given class, either positive or negative. So we are going to rely a little bit on this concept of multiple instance learning to build up our two solutions. So let's look at this multiple instance learning a little bit in a closer look. So there have been some methods that proposed this for the case of mammography classification in 2017. And what is so great about this, that you could actually do weakly supervised segmentation, or at least weakly supervised classification of the images that you're observing. So you got an image, and we know the class of the full image. We don't know which regions are responsible for giving that class, or we don't know which are the regions that are abnormal, but we could still split our image in small patches. And this will allow us to keep the high resolution content, which otherwise can be difficult to classify. And we are going to pass that through your favorite network. Here we put as an example, for instance, the ResNet 22. You can predict with this ResNet a series of probabilities of the different regions. And then at the end, you're going to do a pooling operation, for instance, a max. So you take the maximum probability of this. And this is what you're going to compare with the actual label that has been given to the image. So you take the maximum out of all of this, and you can train your ResNet in a weakly supervised manner. So you will get afterwards, during test time, a probability for each of your patches, whereas for training, you only had image-wise labels. So this is the weakly supervised part. Okay, so we start again from our initial diagram, where I'm talking about this intermediate layers as one way to see them is as class activation maps, and another way to see this graph is as a multiple instance learning approach. So our goal now is to learn to classify, but also to segment the abnormalities from these image-wise labels only. So I only know if the image is positive or negative. And as I mentioned, there have been some prior results, and we want to improve over those results. And the first proposition that we are going to make is we are going to try to learn to decompose the images explicitly into a normal and an abnormal region. So if this is my input, I want to have the sum of a normal part plus the sum of an abnormal part to build together this initial original image. And this will help us with the weakly supervised segmentation. So at the end, this is the type of results that we want. It's the regions that are responsible for making the decision, but a higher resolution. So one thing to be noted here is that I have marked in these images these borders. What I'm putting here as borders are annotations that have been done by doctors, which we need in order to evaluate if our segmentation is actually doing well or not, but these annotations are never used during training. So you can only build a database maybe of a few elements such that you can evaluate if your method is performing well or not. Okay, so the second proposition that we are going to do is to bring prior knowledge about the abnormalities. So what is interesting about mammography is that because of this screening process in which women are encouraged to do mammographies often, we can have very large databases of normal images. So the good thing is that we have images. The bad thing is that they probably don't contain the parts that are interesting for classification of breast cancer. But anyway, we do have these normal images, and what we can try to do is to bring some prior knowledge about what we know about these abnormalities to simulate abnormalities over these normal images. So once we have these normal images, we can try to do to use an unit like architecture to segment the content of this image, and we are going to do this in an explicit manner. So we are going to really not only try to predict the mask, but really separate the content into the normal and abnormal part, as we mentioned in the previous slide. So what do we know about these abnormalities? We have, for instance, masses that look like this, or distortions that create some sort of radial distortion, and then we have calcification clusters that are usually characterized by hyperintensities and a group of hyperintensities. And this is, for instance, one of the hardest to catch if you keep low resolution images, because these clusters can be, the hyperintensities can be very small. Okay, so we have two propositions now. The idea is to bring them together. So we have a benign image, we have a simulated abnormality, and then with this, we build a data set that, without any annotation costs, allow us to train a network into separating normal and abnormal parts. So for the technical part, we are going to use a part which is a reconstruction of the abnormality. So we are going to compare the mask directly to the simulated abnormality. And then we are going to also use a regularization, additional auxiliary cost function, which is going to compare basically that the image, the sum of these two, builds up again to the benign image. So this is one part, but we have also the class activation maps that we were talking about in the beginning. So what we propose is to combine the two because they have complementary information. So we are going to use this abnormality masks that we are extracting from the segmentation part as attention maps for the malignancy. So how does this look like in practice? We had our classifier, or typical classifier. I'm just looking at the fully convolutional, the last fully convolutional layers of my classifier to have this weakly supervised localization. This part, I'm going to train it for a specific classification of malignancy, whereas here I'm just training for abnormality. So these two concepts are different. You can have masses that are benign, for instance. So here I focus on detecting any abnormality. I pass my segmentation to the classifier part. I do a simple product of the two, and I train this part of the classifier to decide whether this abnormal part of my segmentation is either malignant or not. So you see here, I haven't created any new network. I have basically used a unit that you might have been used to and a classifier, some classifier layers that are just convolutional layers. So it's just the fact that we are explicitly trying to look for things that we know that is going to help us get better results. So what else can we do? We can bring additional prior knowledge. For instance, I can control the lesion size. And for this, if there's something of interest in your application, you can look at this original papers where they give some notions on how to control the output of your segmentation. So we know from statistics, from clinical papers, what are the typical lesion size of masses, clusters, and so on. So we can penalize anything that is coming out of our segmentation and that falls outside of the desired lesion size. So if you're below a normal lesion size or above a lesion size, you'll get a high penalty. We can also control things that we know as the typical lesion number and the distribution. So for this, we can use morphological based losses that are now also possible to implement in a differentiable manner. So for instance, we would like not to have holes inside our segmented lesions, and closing operations are typically known for getting rid of such holes and gaps. So we could use things like closing and also maybe getting rid a little bit of the noise. So there are also morphological based losses that let you get rid of small activations in the bottom. So we can include this losses because we know from prior knowledge and from discussing with the doctors that these things are not going to occur. So we can try to enforce our segmentation to focus on the important part and not on artifacts. Okay, so here are the two, the closing and the top hat. And this is a full view of the full approach. So we have now classification loss that focuses on telling you whether the abnormality is positive or negative, or malignant or benign. Some reconstruction loss that helps us in the training of separating the abnormal and normal content, and then some additional losses that control the size and distribution of the lesions that we segment. So in practice, when you have your data and you have this network, what you do is first a self-supervised training. So here is where the self comes from. We are basically pre-training this unit-like architecture to learn how to separate these two things first, only from these simulated abnormalities and from normal images. And then in a second stage, we are going to refine what is happening here with these additional layers for classification with a weekly supervised training. So here we are going to include the mammograms that are not only benign, but also those cases that have proven breast cancer lesions. And we are going to retrain this part and this part in order to get our final prediction for the image, and also this malignancy or this abnormality map for the interpretability of the decision. So these are some results on how you can modify what you actually get from a network when you add such prior knowledge losses. For instance, here is when you combine all of the losses, and you can get the pink is the actual mass and the blue are predictions. So you can see, for instance, that we are getting rid of this border predictions around. You would maybe say that this is actually the best solution because we have blue only where there is pink, but of course this is only on a single image. And globally, when we evaluate the performance across the full data set, this image here, even if it has some false positives, this combination of losses turns out to be the best solution. Okay, so some quantitative results. So here we compare basically classification results. And what we are going to compare is if we have what type of supervision we're given to get these results. So here, for instance, if you want to get the best results, you would need a doctor to exactly point in your image where the lesions are. So this is full supervision, the ones that are still up to today getting the best results. But if you have, as in our case, not access to such delineations, then these are the results that that we can compare to. So in our case, we're actually somewhere in between the prior work, full supervision, and weekly supervision. So by the designs and the losses that we are including, we are getting improved results. So for concluding this part, we have comparable classification, localization, and segmentation performance versus fully supervised training. I mean, for the classification, there's still a gap we have to break. We don't need any expert annotations, and we can deal with images at high resolutions. And one important thing is that we show how to, if you have access, for instance, to benign data and prior knowledge of what is the abnormalities that you want to find in your images, then this is actually a good source of data for your networks. So the self-supervision is something that you may try in your own applications, as well as this multitask learning to control the output predictions. What is not so desirable about this method is that we still have to tune the different hyperparameter losses. So you need some sort of knowledge of, for instance, the size of the lesions, and does not really consider the context around the lesion. And I'm going to talk about just that in the second work. So this is a continuation of the work with a colleague of ours here in the lab, Mira Rzkala, and Guillaume, which is a PhD student who started recently. So we are going to take a different path here. We still try to do this benign malign classification. So on the left, the benign images, you see that here we have, for instance, an abnormality, but it's still considered benign. And what I have mentioned before is that these methods that perform best so far, they usually go through 2 steps. So they need a doctor to annotate exactly where the lesions are and tell which parts of each image are positive. And in this way, you can train, for instance, a detection architecture, which will be able to put a bounding box around the regions of interest, and this is fully supervision. So once more, we don't have access to such annotations, which are quite costly. And also, if you don't detect a lesion, then basically you cannot tell if it's positive or negative, so you cannot recover from the undetected regions. And once more here, although you keep the high resolution because you create patches around your detected regions, the problem is you will treat each region separately. So what we are going to do here is to come back to our multiple instance learning approach, where we had our image and we divide it in patches, and we pass it through a classifier that would give you some probabilities to each of the patches, and take the maximum to be able to compare to our image-wise label. So we are still in this weekly supervised training, but we are going to change it in a different manner. So what this multiple instance learning are typically doing is that they don't have really non-overlapping patches. They have some overlap, but the patches do not have anything to do with the actual, the border of the patches does not have anything to do with the masses or lesions that you can encounter. So what we want to enforce is that the regions that we are analyzing are actually regions of somewhat homogeneous texture. And for that, we are going to rely on a superpixel grid. So for those who are not aware of what a superpixel is, it's just a collection of pixels that is done using an unsupervised clustering approach. Typically is called SLEEK. And we are going to be able to separate regions of interest that we are then later going to analyze. And we are going to do this separation not only on a single scale, but you can see here I have done the same process, but the superpixels are smaller so that we can capture as well the clusters of calcifications that are quite small or the masses that could be large. And the second thing that we are going to change is that we are not going to treat a regular grid with a CNN. Here you see that all of each of the patches has exactly the same neighborhood. So there's no information included in the topology of such grid. Instead, what we're going to do is to create a graph that connects the regions that have been segmented with the superpixels. And we are going to do this on a single scale and across the scale. So we are going also to connect across the scale. We're going to create a big graph and use instead a graph convolutional network to aggregate the information. So if we start again from the mill approach, what we're going to do is to change the input. So it's not going to be this regular grid, but we are going to do several scales of superpixel clustering of the images. And then we are not going to get this type of result, but we are going to pass directly the graph that we are building from our segmentation to a graph convolutional network. So for those not familiar with a graph convolutional network, this is an extension that is able to compute convolutions on non-regular grids. Basically, there are several approaches to that, but I don't have the time today to go into the details of how this exactly GCN works. And once we have the GCN, what we are going to do is at the end of some, in our case, we are going to use four graph convolutional layers. We are going to get a graph that has now communicated through the connections between the different regions. The topological information, we can then do exactly the same as before on the nodes of the graph instead of the patches that we had before. We are going to aggregate the probabilities, and that's what we are going to compare with the image-wise labels. So we're going to compare image-wise labels with the max of the probabilities predicted for each of the nodes of this graph, where these nodes are going to be interpretable, as I'm going to show a little bit later. So the goal would be the same. We want to find and segment the malignant abnormalities on mammograms, and we are going to consider datasets with only image-wise labels. So if you see any annotation, this is only considered for evaluation of our method. We are going to deal with high-resolution images with lesions of various sizes, and we are going now, different from our previous work, to take into account the context or this topological information I was talking about. So the important thing about the context is that when there are lesions occurring, let me go back here. When there are lesions occurring, actually, they might change the number of neighbors and the closeness of the neighbors than when you have homogeneous regions. So this is the type of information we're trying to capture here. So let me go back. Okay, so let's go a little bit into the different steps of the method. So we have first to build our graph, then to extract features for filling the graph, and then we just apply this graph convolutional network. So for the building of the graph, as I mentioned, we are going to apply SLEEK, and SLEEK is going to ask you about the desired number of scales. So how many of these oversegmentations do you want? And there is actually a rule of thumb to decide given the minimum and maximum size of the lesions or of the objects that you are going to find. So there's a rule of thumb that will help you decide how many scales and what is the size of each scale that you want to give as input to this algorithm. At the end, so we are going to have here 3. We tested up to 4 different scales. And once you have done this, you're going to connect every region to the neighbors. So this is how we connect in a single scale. And we are also going to connect across the different resolutions. So for instance, if here I have a superpixel at the course's resolution, then I'm going to connect this superpixel to all of the superpixels that are overlapping at a finer scale. And again, this one at a finer scale. And this is how we build for each of the nodes in this course resolution, the connection to the other nodes. So at the end, what we are going to have as output is going to be a graph with vertices and edges, and it's going to be a multi-scale graph because we connect the different scales together. So the second part is how do we field the nodes of this graph? So this graph is an attributed graph, so it means that each node has also, for each V in this set of vertices, we are going to give a feature vector, and this feature vector you can use your favorite network, or it could be even radiomics features. So you can connect here for each of your superpixels, you're going to extract features. In this case, we use the ResNet actually from our prior work to extract the features. And we also added to this feature vector the coordinates of the barycenter of the superpixel. So in this second stage, we just have our graph, and we are going to fill it with attributes about what is inside of each of the nodes of this graph. And then the third and final part is we have our graph, and we have the attributes here denoted with these different vectors. This is our input to this final part, and then we are going to apply a graph convolutional network. Here we use the simplest graph convolutional network with message passing and with 4 layers. We are not even using attention for this work. And we are going to then transform basically this graph into some, here you are going to use the features on the nodes as well as the topology of the graph to change at each layer the attributes of the nodes. And by changing, by message passing and by applying this GCN, basically the idea is to convert the features that are processed for each network into something that compounds or mixes the information from the features and from the topology. So once you have your final graph and your final features, then we do again a max pooling as we have done for the previous works, and are able to obtain once more prediction whether there's malignant or normal. And when we can also look at is that this, similar to the class activation maps, we can look at this graph before doing the max pooling, and we can color code it to see which regions are now responsible for the decision before the max pooling. So here we are denoting with, I think I have another slide on that, yes. With high intensities, the regions that are most likely malignant, and with black, the regions that are most likely normal. So you have your prediction for the full image, as well as these maps on different resolutions that you can look at to see in a more trustful manner the shape of the regions that might be of interest. So we tested this on a public data set and a private data set with different vendors. And in each case, we are going to use these region-wise annotations just for validation, not doing training. And what we see is first we do an ablation study. So we're going to progressively add different features of our method to see if they have actually an effect or not. So the baseline will be the multiple instance learning approach, which is just the ResNet with a single scale. And then we are going to, instead of square patches, do superpixels. So with 4 scales, so we add the scales and the superpixels, and this we call BSP. And finally, we also add the GCN, which will aggregate the topological information on top of the ResNet features. And what we observe is that as we add either the superpixels or the superpixels and the GCN, we largely improve specifically the detection rate. So classification gets a little bit better, but what is really increased here is the detection rate. So we are much finer at detecting which regions are responsible. And here we also compare to the state of the art. So once more, if you have the annotations, of course, you're going to still get better results. We are having still a gap with respect to those, but the detection results are actually better than the fully supervised case that reports the higher results so far, which is still from 2018. And we have similar results, so also a compared method from MEDIA in 2020. Okay, and these are some qualitative results. So here we have what you would get as a class activation map with the simplest method, which you see is very pixel-based. This is still a good detection, but it does not really relate to the anatomy. And then you can see for one scale and for second scale, what are the predictions. And then you can also, we play a little bit on how to aggregate the results for different predictions. I think there's still interesting work to do at this level to come up at the end with some segmentation, for instance, of a cluster of classification or of a mass. So we are reaching here the detection results. So in this type of curves, you have true positive rate versus false positive per image. And ideally, you want to be here. When you're fully supervised, you're here in this blue star. And here we get this type of results with our method. Okay, so here we have shown a graph representation that allows to handle lesions of different sizes that it helps improving interpretability and that keeps this topological information. And we also mix this with multiple instant learning on the graph and relied on a GCN to better aggregate the features and topological information to improve the results. Okay, how am I doing on time? How much time I have left?
Well, I would say 5 minutes easily, probably even 7. We can have 10 minutes for questions. Okay, that should be fine.
Okay, so that would let me explain the second concept that I'm a bit excited about. So this is about another PhD student. She's just finished in July. And she was working with COMULIS and the Institute of Cancérologie del West. So the problem here is a little bit different. We want to monitor treatment response in metastatic breast cancer. So in PET, CT images are usually used for such monitoring. So you get initial acquisition, and typically after 2 months, you get a follow-up. For the cohort that we were using here, which is a prospective study, we were able also to get an in-between first follow-up after 1 month. So what doctors are encouraged to do is to follow criteria like the PERSIST, where they are going to look at the most fixating lesion of the patient in the initial acquisition, and they're going to look, for instance, as the highest value or the region with the highest value, and they're going to look at this different intensities, and they're going to compare them between initial and follow-up. But you can see that here, for instance, the lesion that is being looked at is not even the same lesion, but they will still focus on a single lesion at each time. They are going to also check for new lesions, appearing lesions, and the quest here is of this type of criteria is to determine if the patients are responding to a given treatment, if they are progressing, or if they are stable. So you can imagine that this is quite operator dependent. We are dealing with volumes. You have to scroll through the volumes, and focusing on a single lesion is probably not ideal. The response could be, for instance, heterogeneous across the body. So what we want to start dealing here is automatic follow-up. So assisting the doctors with how to automatize this process when you have so many things to look at. And what we figure out is that this problem has really been scarcely treated in the literature. There is, for instance, a recent paper in RSNI radiology exactly pointing to this fact that we don't look at a follow-up problem, which is actually what you want to probably help really doctors with. And here are some examples to show you the type of heterogeneity that we can find. So you can see that there are people with a few number of lesions, but there can be also heterogeneous responses, like here. Some regions seem to be responding and some others not. So the challenge number 2 that we are dealing with is, again, the doctors do not segment on their clinical protocol the lesions. And you can imagine that if there are many, this is going to be even more tedious. And moreover, there is no, in the clinical records or in the protocols that they are following, there is no time to basically establish correspondences lesion per lesion. So this is really difficult to obtain. So what we are going to try to do here is trying for our database to monitor this metastatic breast cancer with as propagating initial segmentation. So we are going to assume that we have either an automatic method or an operator that takes the time to segment the initial lesions, and our quest now is to see where did these lesions go after treatment in the first or second follow-up. And moreover, we are going to actually formalize this propagation in terms of a volume registration problem. So we're going to deform the first image to try to match the second and find a dense correspondence map between the two images. So here's again, so we are going to have our initial image and a follow-up image, and we're going to apply some image registration to deform the initial image and make it look as much as possible as the follow-up image. Once we have done that, we have a deformation field here that we can apply to our initial segmentation so that we have the location of the masks in the new follow-up image. So what we are going to propose here is a little bit unconventional, is that we are going to use a deep image prior to model the deformation field. So this is what we are going to include here. And to actually explain what this is, I'm going to first go to the conventional registration methods. So when you are trying to register two images with conventional optimization methods, what you're trying to do is find a deformation field that is going to, that once you warp your image with, are going to bring this moving image to look as close as possible to this fixed image. And you are going to optimize the parameters of this deformation field. So you can model this deformation field either fully deformable for deformation field, or you can use a transformation. And to find it, you're going to minimize a cost function that is usually a similarity between how the warped image looks with respect to the fixed image. You want this to be as close as possible. And then sometimes we have this regularization terms in order to control how this deformation field looks. So a typical conventional registration method uses the formable, for the formable transformation uses, for instance, normalized cross correlation as the similarity between the two images. And for the regularization terms, it might use smoothness or anti-folding regularization terms. And you can optimize such cost functions using stochastic gradient descent. So what is happening in the deep learning world with respect to registration? So we are at the moment where we are starting only to reach the same level of performance. And this is one of the topics where actually not a segmentation or classification, where deep neural networks overperform the other approaches. Here we are not at that stage yet. And how a deep learning method for registration works is that you will have a database of moving and fixed images, and then you want to predict a deformation field with exactly the same type of cost function and regularization. But here what changes is that your transformation now is given as the output of a neural network. And then once you have trained your neural network, you basically use the parameters that you have found in order to warp a new moving image into a new fixed image. So what is different from ours is that we want to try to bridge a little bit the gap between these two type of methods. So we are going to place our proposition method, which is called MIRBA, as somewhat in between. So as you see here, as in the case of conventional optimization, we are only dealing with a pair of images at a time. And as with deep learning, we are using the neural network as a model of the transformations that we want to predict. So why doing this? So we didn't come up with this idea just like that. We are relying on a concept that is called deep image prior that was introduced in 2020 for denoising. So here you see, for instance, the image of an image that has been corrupted by JPEG noise. So if you look close at this region, you might see some black or gray regions that shouldn't be there. And what this deep image prior proposed is that you're not going to use neural network to denoise by learning on many on a database, but you're just going to use the image that you're going to denoise. So you're going to put, for instance, Gaussian noise as input to your network, and then you're going to, with the cost function, bring the prediction of the neural network as close as possible to the input image. And what you're going to see is that the predicted image, as you progress in this training, is going to get closer and closer to the output image. And if you find the sweet spot of the number of iterations, then you will see that here the JPEG noise has been reduced. So you're going to do this by just optimizing for cost function that is a similarity between the predicted image and your original image. And the change of paradigm here is that your neural network will fit a single image. So there is no test phase, there is no training database. So what is interesting here and why is that important for registration is that what we are claiming with this work is that this neural network is actually bringing some sort of implicit regularization that is not being fixed as a regularization term in a cost function, but it's just by the fact of that is letting you or not model certain deformation fields. You're going to be able to get better results if you use convolutional networks to model images. So if we compare, the point I'm trying to make is about this implicit regularization. So usually you would have, for instance, when you do a conventional image registration, you still have that type of regularization, implicit regularization, when you choose, for instance, some splines to determine the regularization field. When you use deep learning, you also bring some implicit knowledge or some implicit bias by including a data set. So if your test image is outside of the domain of the data set, you will get not such nice results. And what we're doing here is that we are getting rid of the bias from the data, and we are just trying to use the architecture as a means to better model the deformation field. Okay, so these are just the same concept in more details. In practice, what type of architecture we use? So here we are relying on prior work, where these were the winners of the one registration challenge that occurred in MICAI 2020, and where they really tried to replicate as much as possible what we know about conventional registration methods in order to put those terms in terms of an architecture. So actually it's composed of a course-defined composition of unit-like architectures. All of these layers are convolutional, and then you have some residual blocks in the middle. You use typical neural normalized cross-correlation as similarity, and typical regularization terms as the smooth term and the non-unfolding term. So the type of evaluation we do is on this 110 pairs of images. And as you will see in the paper, if you're interested in this work, we have tested 23 configurations in which we really try to evaluate the impact of every network component. We evaluate different types of inputs, different types of losses, explicit and implicit regularization terms. And we compare to conventional and to deep learning methods. And we propose various metrics. So when we have segmentation of lesions and organs to compare with, and also direct registration measurements like the TRE or the Jacobian of the determinant of the deformation field. So the conclusions, without going into much details, are this is our approach. This is what happens if you measure without any registration. So any of the methods that are proposed will improve the results over no registration. When we compare to conventional fields, conventional methods, we are second best to the two that we chose. So we are not yet, we cannot claim that this is going to be better than conventional methods, but we are closing the gap. And when we compare to deep learning methods that use a database, so Voxelmorph and Laprin here are using a database for training, then we see that we get better results than those. Of course, the price is that we do this at much a slower rate. And when we compare the course to find the type of architecture, so one of the experiments that we did is whether we need 1, 2, or 3 levels of deepness, and you see here the results. So you see how progressively in the first, this is no registration, this is with one layer, with one level, 2 levels, and 3 levels. You see that they match quite nicely. And there is also some interesting work now on the math side, justifying the deep priors to solve inverse problems, and that tell you that usually what you are going to do in each of these levels is treat the image with low pass filters, progressively higher pass filters. So this is actually a nice feature for registration. And finally, when we compare the regularization terms, so the big question is, how much is better to put the regularization as implicit inside of an architecture or as explicit as a term in the loss function? And what we show here is that best results are obtained when we do this implicit architecture. So we compare here our approach versus supervised approach versus using only the architecture in this column or using only the regularization terms. As you see, the performance drops more when we remove the regularization that is brought by this by the architecture. So this confirms our idea that it's a good idea to use convolutional neural networks as generators for deformation fields. Some qualitative results, so from a disappearing lesion, reduction, and a lesion that is being reduced, some stable lesions, and some lesions that grow. And to conclude, so we have shown a parallel between conventional and deep learning registration methods, putting us in evidence these implicit regularization terms. And with MIRBA, we proposed a registration with a neural network as transformation model that is optimized only on a single pair of images, and that is especially adapted for registering objects that occur in different locations. And in progress, we are also trying to validate this more clinically to see the impact of this. Okay, so as I had foreseen, I won't be able to talk about this, but since you probably might have access to the slides afterwards. So my motto is small data sets and few annotations. And how do we cope with this? Adding prior knowledge in different manners. For instance, we saw prior knowledge in appearance, shape, or context, or also prior knowledge that is implicit in the architectures of deep networks. I'll let you some references on the slides on other type of works that are dealing with similar problems and other solutions for coping with those. So thank you very much. If you have questions.